In this video, we'll wrap up our discussion of thermochemistry by looking at Hess's law and talking about heats of formation for a reaction. So first, let's look at heats of reaction. So if we know we write an equation, we can assign an enthalpy value to the heat associated with that reaction. In this case, with the positive enthalpy, we know that heat is going to be a reactant, so we might write it like this. So first, what we want to talk about is how if we have a reaction and we modify it, how that might change the delta H for that reaction, similar to what we did for looking at equilibrium constants. So in this case, if we multiply the reaction by 2, we can think about what happens to delta H. So if we look at multiplying the reaction by 2, we'd have our heat plus 2N, so we've doubled the moles of N, we've doubled the moles of O2, and we've doubled the moles for NO. So when we're thinking about this heat in this case, remember when we're giving these delta H's of the reaction, it's implied that this is included with the stoichiometry. So this means this is plus 180 kilojoules for every mole of N2, for every mole of O2, or for every 2 moles of NO. So if we multiply the whole equation by 2, we now have 2 moles of N2, for example, by 180 kilojoules per mole of N2. And since we multiplied everything by 2, we'd get that the delta H is going to be multiplied by 2. So if we multiply the reaction by 2, we'd multiply the delta H by the same value. And this is going to be true for anything we multiply an equation through. So if we multiply this equation through by 5, the delta H would be multiplied by 5. And likewise if we used fractional versions of the equation. Okay, let's look at another example. What if we take this reaction and now we flip it? So this is a little bit different because we still have the same ratio of everything here as we did in this sign, but notice by reversing the reaction, we took heat and switched it from being a reactant to now being a product. So we know that if this reaction requires heat, the reverse reaction is going to release it. And so that means this reaction went from being endothermic to being exothermic. So it's going to have the same magnitude of energy, but we'll be releasing instead of absorbing it. And so we flip the sign. So the delta H in this case is negative 180 kilojoules. So if we reverse any reactions, we flip the sign of delta H. These two features lead us to Hess's law. Hess's law is a result of both the conservation of energy, so the fact that energy can't be created or destroyed, which allows for all these different versions and swaps of the enthalpy equations, and also a result of the fact that delta H is a state function. So what Hess's law states is that delta H is the same whether the reaction takes place in one step or several steps. So if we can break apart an equation into individual steps, we can just add together the delta H for those individual steps and then get the delta H for the overall reaction. Let's take a look at this. So say we have this reaction here, N2 plus 2O2 going to make 2NO2, and we want to know the enthalpy of this reaction. Well, say we can't measure that, but say we do happen to know the enthalpy of the reaction of going from N2 plus O2 to make NO instead of NO2, and we also know the enthalpy of NO2 going to make NO plus half an oxygen. So if we have these two given bits of information, we can use Hess's law to calculate the overall enthalpy. So I'll give you a moment to think about it and choose your answer. Okay, and the answer in this case is C. So how do we get to C? Similar to when we did this with the equilibrium problems, we need to see how we can combine these two equations to get to this one. And we can see that for the top equation, N2 and O2 seem to be on the side that we want them on. So it looks like we'll leave the equation number 1 alone. But for this one, we can see NO2 here is out front. We want it to become a product. So maybe we want to reverse this one. And you can also see the number here. There's a 2 in front of the NO2 and nothing here. So maybe we want to reverse and times 2. If we did that, we end up with 2 times half an O2. So that's just another O2. 2 times NO, that's plus 2 NO, going to make 2 NO2s. If we check out if this works out, it looks like our 2 NOs will cancel, which is good. We'll end up with 2 O2s, which matches what we have in the original equation, an N2, and a product of two NO2s. So it looks like reversing this and timesing 2 gets us what we want. So for the delta H, we have to change the sign, so it goes from positive to negative, and we have to multiply it by 2. So 2 times 56 kilojoules gives us negative 112 kilojoules. And so if we combine these two equations, that's the application of Hess's law. So we can combine the two delta H's to get the overall delta H. 180 minus 112 gives us 68 kilojoules. So the last application of this goes to standard enthalpies of formation and how we can use these to calculate standard enthalpies of a reaction. So the nice thing about this, thermodynamics and state functions and Hess's law, means that without having to go through and do calorimetry for every single thing that we can imagine, we can actually approximate the energy of a reaction before we've ever run it using a few principles. First, we need to define what we mean by standard. So this little knot that we see in front of the H means that it's under standard conditions. Standard conditions means that all gases are 1 atmosphere and all solutions are at a concentration of 1 molar. So remember, this isn't quite standard temperature and pressure. So standard, this little thing, does not mean STP. It just means everything is 1 atmosphere or 1 molar. The little subscript here of F means formation, which means something very specific. So it means that we are forming exactly 1 mole of a compound, and we're going to form it from its elements. So the standard in this case means that we're forming 1 mole of the compound. And since we're forming it, it's going to be exactly from only elements at 1 atmosphere and at 25 degrees C. So this has some STP and some standard in terms of it being 1 mole in these equations. So let's look at an example of tables of standard HF values and how to read these. So if you look this up in your book, you'll see something like this. It gives you the delta HF for a bunch of different species. Now we need to think about how to read this more precisely. So, for example, if we're looking at NH3, because the standard heat of formation means we're forming exactly 1 mole, that means if we're writing this equation, we'd have 1 mole of NH3 in the products, and we need to make it from elements. So remember, nitrogen and hydrogen are diatomic elements, so we have to use N2 and H2, and this is why we sometimes see these weird fractions in equations, because in order to get this to work from just elements, we have to use fractional versions of H2 and fractional versions of N2 to get exactly 1 mole of NH3. So this value right here means negative 46 kilojoules per mole of NH3 formed, but that also means in order to do that, we have to use half a mole of N2 and 3/2 of a mole of H2. You can see the appendix in the book. It lists more compounds that are listed here, but just so you can see more of these tables and these enthalpies of formation. So let's practice interpreting this a little bit. Look at these following, and which of these equations would actually correspond to a standard enthalpy of formation for water? And the answer is C. Let's look at what's wrong with the other ones. So in this case, we're making 2 moles, not 1 mole, so that's not a standard enthalpy of formation. In this one, we are making 1 mole of water, that's good. We're using H2, that's an element, but O, remember oxygen exists as a diatomic element, so this is not correct for the standard enthalpy of formation. We have to use the normal standard elemental form of oxygen. So this is also not the right equation for the standard enthalpy of formation for water. It's going to be this one right here, where we have to use this 1/2 in front of O2 to get our 1 mole of H2O. Let's look at another example of this. So for these different types of ones, which of these could be a valid standard formation reaction? And the answer is D. Let's look at what's wrong with these other ones. Here we have N, which should be N2 in its elemental form. Here we're making 2 moles of HF, not 1. And here we're making calcium sulfate from something that isn't elements, so that one is ruled out. This last one, we have our equation that we already said was good for water. So just D is valid in this case. So the major conclusion from this whole section is that we can calculate enthalpies, so determine the energy for a reaction, which we know is important for lots of things like fuel production and things like that, without ever having to actually run the reaction in a calorimeter. And we can do this by using Hess's law and these standard heats of formation, because we can combine standard heats of formation And so we can find the standard enthalpy of a reaction by looking at the heat of formation of all of the products and the heat of formation of all of the reactants to combine them to get an overall delta H for the reaction that we're thinking about. This notation here, we're just using these sigmas as a sum, so we have to sum the heats of formation for all of the products, and we have to subtract the heats of formation for all of the reactants. This comes from the fact that, again, normally when we are making something happen, we have to break apart all the bonds in the reactants and reform them in the products. So let's look at calculating the delta H for this following reaction. To do that, using some standard heats of formation, here's a table with some listed values, and we can start setting that up. So for the products, here I have our HNO3 and our NO. One thing that you'll want to be careful with when you're using these tables, so this one is set up kindly for us, but sometimes we have options for phases. You want to make sure the phase matches. Heats of formation can be different under different phases, and actually these two should both be listed as gases. So for the NO3, we have our product, and it's negative 207.4 kilojoules per mole, and since there is a 2 in front of it, we need a 2 times that. We have to add our other product, that's NO. So here's our NO. We only have one of those at 90.3. And then we have to subtract the reactants. So we have 3 of the NO2, that's 33.7. And we have 1 of the water, so 1 times negative 285.8. And if you plug all these in, you should get the delta H naught for this reaction of negative 139.8 kilojoules. So using a list of some empirical data, we can find out the enthalpy of a novel reaction just by applying some of the results from Hess's law.